We were tasked with measuring the health of Matanzas Creek at Hoen, and there were two words that described our journey.
I have two words for you. Don't say it, Risk. Don't say it.
In terms of chemistry, the health of a creek is determined by finding the overall water quality index, which is found by taking into account a wide array of chemical tests, including dissolved oxygen, fecal coliforms, pH levels, biological oxygen demand, temperature change, total phosphate levels, nitrate levels, turbidity, and total solids. Each of these tests is then compared against a graph in order to find its quality value Q. Then, all of the Q's are weighed by their relevancy and added together to determine the overall water quality. Dissolved oxygen can be lowered by drought, the buildup of organic wastes, and major shifts in the types of aquatic life. Our dissolved oxygen saturation rate of 29.1% indicates that a large amount of plant growth is consuming much of the oxygen in the system. Fecal coliform indicates organic waste buildup, and a too high value indicates an abundance of pathogenic organisms. Our value of 7 colonies per 100 milliliters was low, meaning the creek is healthy in this department. Biological oxygen demand measures the quantity of oxygen used by microorganisms when oxidizing organic matter like dead plants. Although the value for this we got was inaccurate, negative 3.5 milligrams per liter, the value still matters when finding the quality of the creek. The pH of the creek was 6.02. pH can be affected by smog pollution and acid rain, and normal values are between 6.5 and 8.5 pH. So sadly the creek is slightly acidic for natural water. Temperature change can affect other measures of health like dissolved oxygen, so a relatively low value of 1.5 degrees Celsius is a good sign for the creek's health. The phosphate value indicates the addition of waste products that add to the normally scarce amount of naturally occurring phosphates. Our value of 0.335 milligrams of phosphates per liter is very low, so there's little pollution in the creek. Nitrogen is needed by all living organisms in order to synthesize proteins. If nitrate value is high, there's pollution in the creek, generally marked by eutrophication and a large growth of algae. Our nitrate value of 1.4 milligrams of nitrates per liter was fairly low, so again there isn't much pollution. Turbidity measures the overall clarity of the water, with high values indicating a loss of ability to support organisms. Our turbidity value of 12.0 NTU was consistent with previous years and fairly average. Total solids in a creek indicates the amount of decaying plant and animal matter as well as the amount of soil erosion, leaves, urban runoff, and other pollutants in the creek. 70.63 milligrams of solids per liter was fairly low and indicates little soil erosion, little animal byproduct runoff from the farms, and little urban runoff. After finding all of the Q values, weighing them, and adding them together, we got an overall water quality index of 65.18. State standards require it to be between 50 and 58, so ours was average. Previous years were similar. 2013 had 82% and 2010 had 77.85%, so our results were at least semi-accurate. However, it seems the overall water quality is declining, probably due to the drought. With dissolved oxygen being so low, something might have been introduced to the creek that is now consuming all of the oxygen. The biggest issue for the chemistry portion was probably calibration, with almost every test requiring a probe to be calibrated for whatever the test was. There were also no riffles in the creek that day, so we had no riffle data. This probably affected our water quality index, as riffle data would have most likely created a higher water quality index. Overall, the Hoen portion of Matanzas Creek when looking at the chemistry is moderately healthy, though declining most likely due to the drought. The bio portion dealt with Daphnia, a species of small planktonic crustaceans which reproduce asexually. In a healthy environment, Daphnia populations increase at an exponential rate. However, when in a poor environment, Daphnia tend to suffer horribly. Our fine biologists went out and collected samples of creek water and brought it back to the lab, as well as various leaf samples from around the creek. The leaves were then dried in between sheets of wax paper. In the lab, 10 cups were filled with 200 milliliters of water. 5 with creek water and 5 with generic store-bought water. Each of the cups were oxygenated and then filled with 12 live Daphnia magna, meaning on day 0 there are 60 total Daphnia for both creek and store water. The cups were stored in a safe place and the Daphnia got their business on. Every other day the Daphnia were fed with algae solution and their water was oxygenated. After 2 days the Daphnia had not grown at all, staying at 60 total for both creek water and store water. After 6 days, both counts rose to about 70 total, and after 9 days both counts jumped to about 180 total, with the creek water having slightly more. While the Daphnia grew a bit more in the creek water, it wasn't substantial, and is probably attributed just to the creek having a bit more natural nutrients than the store-bought water. This conjecture that the creek water was a bit better than the store-bought water could be supported further if we had riffle data. But there were no riffles. As a result, we can't fully compare these results to those of previous years. For errors, it was practically impossible to determine the health of each of the Daphnia before choosing. Ideally, they would have been all equally healthy, but that's notoriously hard because the Daphnia are small and rather erratic. Additionally, we used a pipette to put the Daphnia into the water, and larger Daphnia couldn't fit into the pipette, and using anything larger than a pipette would have added too much foreign solution into the cups. This means the smaller and medium-sized Daphnia were more favorable, making the experiment a convenience sample. And, just like the other groups found, there are no riffles in this section of the creek, meaning we didn't have a fully comprehensive evaluation of the reproductive conditions of the creek. For the physics portion of the lab, we got to measure and model the creek itself. We started by measuring out the entire length of the creek with our handy yellow measuring tapes. Luckily, the entire length of the stream was in a straight line, so we didn't have to take multiple measurements. Then, we needed to figure out the width of the creek every 2 meters, meaning we got to traverse the entire length of the stream again, only it had also started raining. With the length of the creek and a rough idea of its width, we were able to make a top-down map of the creek. Finally, we chose 4 sites along the stream bed equidistant apart and measured their depths. Since the stream wasn't very wide, we chose to measure a depth every 25 centimeters. This means we got to go down the entire length of the stream a 3rd time, in the mud and in the rain. So we had to decide who would do it. I think Evan best sums up our experiences that day.
This is the worst day of my life.
We then drew what we measured of the depth. We also needed to measure the creek's flow rate, but the creek wasn't flowing at all. It was completely stagnant. Overall, the creek looked small, thin, and not very deep at all. It wasn't flowing, and it looked like it was on its way to being totally dry during the summer. As a whole, the creek looked to be in moderate health. It got an OK rating from its chemical tests, and it was able to support Daphnia a bit better than normal water. The creek didn't look that strong, though. It was thin and shallow, and it looked like it could really use a whole lot of rain. Most of the poor things we've noticed, though, are easily and succinctly explained by the drought.